Mercury is a world that defies the simple logic of distance. It is the closest planet to the Sun, yet it remains one of the most difficult places for any human-made object to reach and remain. This tiny, scorched world is located approximately 48 million miles from the Sun. While this is significantly closer than the gas giants of the outer solar system, the energy required to visit it is immense. For perspective, it takes more fuel and complex orbital maneuvering to enter Mercury's orbit than it does to reach Pluto at the very edge of the solar system. Scientists view Mercury as a fundamental mystery that challenges our understanding of how planets form. It possesses an oversized iron core that occupies nearly 85% of its radius, a ratio far higher than that of Earth. This dense interior suggests a violent past that could rewrite the history of the early solar system. By studying Mercury, researchers at agencies like NASA and the European Space Agency can learn about the raw materials that built the rocky planets. Understanding the magnetic field and composition of Mercury helps determine how planets protect their atmospheres from solar forces. This knowledge is directly relevant to our search for habitable worlds around other stars. The difficulty of a mission to Mercury begins the moment a spacecraft leaves Earth's orbit. As the craft moves toward the center of the solar system, it is effectively falling into a deep gravity well created by the Sun. The closer it gets, the more the Sun's gravitational pull accelerates the vehicle to extreme speeds. To reach Mercury, a spacecraft must travel at tens of thousands of miles per hour. However, arriving at the planet is only half the battle. To actually stay there, to enter a stable orbit rather than simply flying past, the spacecraft must perform a series of massive braking maneuvers. On Earth, a car uses friction from brakes to slow down. In the vacuum of space, there is no air to provide resistance. A spacecraft must instead fire its engines in the opposite direction of its travel. Because Mercury is so small, its gravity is weak. It does not have the grip necessary to catch a fast-moving object. If a spacecraft is moving even slightly too fast, the Sun's gravity will simply pull it past Mercury and swallow it. To avoid this, missions like the Messenger probe or Bepi Colombo must perform complex gravity assists. This involves flying past other planets like Venus or Earth several times to lose speed gradually. This process can take 7 years or more just to reach a planet that is relatively nearby. Once a spacecraft successfully enters orbit, it faces an environment of thermal violence. Mercury has no significant atmosphere to distribute heat or provide a buffer against the Sun. This leads to the most extreme temperature fluctuations in the solar system. On the side facing the Sun, temperatures rise to 800 degrees Fahrenheit. This is hot enough to melt lead and destroy standard Earth-based electronics. Conversely, on the side facing away from the Sun, the temperature plunges to minus 290 degrees Fahrenheit. Any technology operating at Mercury must survive being baked and deep frozen every few hours as it orbits. To manage this, spacecraft often use specialized mirrors to reflect sunlight and heavy ceramic shielding to protect their internal components. The proximity to the Sun also means the craft is pelted by intense solar radiation and solar wind, a stream of charged particles that can strip away materials and scramble data. The scientific boundaries of what we know about Mercury are strictly defined by the few missions that have survived these conditions. We know for certain that Mercury has a magnetic field, which is unusual for a planet its size. This field suggests that the iron core is at least partially liquid, despite the planet's small size, which should have caused it to cool and solidify long ago. We also know, through radar imaging and probe data, that Mercury contains water ice. This seems counterintuitive for a planet so close to the Sun. However, because Mercury has almost no axial tilt, the floors of craters at its poles never see sunlight. In these permanently shadowed regions, temperatures remain cold enough for ice to persist for billions of years, protected from the solar furnace just a few miles away. There are aspects of Mercury that remain theoretical. One major theory suggests that Mercury was once much larger, perhaps twice its current size. Scientists propose that a massive collision with another protoplanet billions of years ago stripped away its outer rocky crust, leaving behind the massive iron core we see today. Without more samples from the surface, this remains an educated hypothesis. It is important to debunk the myth that Mercury is tidally locked to the Sun, meaning one side always faces the light. For a long time, it was believed that Mercury did not rotate relative to the Sun. We now know it has a unique 3-to-2 resonance, meaning it rotates 3 times for every 2 orbits it makes. A day on Mercury, from one sunrise to the next, actually lasts 176 Earth days. Another myth is that Mercury is the hottest planet. Despite being the closest to the Sun, it is actually cooler than Venus. Because Venus has a thick atmosphere of carbon dioxide, it traps heat far more effectively than Mercury's airless surface. Mercury is a place of extremes, but it lacks the insulating blanket that creates the runaway greenhouse effect found on its neighbor. From a human scale perspective, Mercury represents the ultimate test of engineering. It is a world where the laws of orbital mechanics are felt most acutely. To visit Mercury is to fight the Sun itself, using the gravity of other planets as a shield and a brake. The abandonment of easy exploration for Mercury is not due to a lack of interest, but due to the sheer hostility of the environment. Every successful mission to this planet is a triumph over the most powerful gravitational and thermal forces in our neighborhood. In the cosmic context, Mercury is a remnant of the violent beginnings of our system. It is a dense, metallic heart of a planet that survived the chaotic formation of the Sun. It reminds us that proximity does not equal accessibility. As we look toward the future of space travel, Mercury stands as a sentinel. It is a small gray world that holds the keys to understanding how rocky planets are born and how they survive in the shadow of a star. The difficulty of the journey only emphasizes the value of the data waiting on its scorched, cratered surface. Mercury remains a silent, difficult frontier, proving that the hardest paths often lead to the most fundamental truths.